we are going to have some total Rekor. We're going to talk about Fuzzing Rekor for bugs and vulnerabilities. Adam is a security engineer at Ada Logic, where his work mainly focuses on security automation. He is heavily involved in open source projects and, fun fact, is a top contributor to OSS Fuzz. Adam, I invite you to come up and take the amazing clicker. And here is your microphone, sir.
Thank you very much. Hello, everyone. My name is Adam Korczynski. This is Fuzzing Rekor for bugs and vulnerabilities. Now, there have been a few of the talks and panels today that have highlighted the importance of using tooling in the process of securing the software supply chain. And you could argue that this is a case study of bringing state-of-the-art dynamic analysis tooling into a Sigstore project. The agenda, why you should fuzz Rekor, how I did it, and some of the findings that came out of it. The reason we should fuzz Rekor is the same reason that we should fuzz any other software application. To find bugs primarily and turn around. If we don't find that many bugs, the good news is that we can verify that there are no or few bugs in the application that we are testing. We also want to test or set up as a testing framework for the current state of the Rekor code base, as well as the future state of the Rekor code base. So Amir Montessori highlighted in his talk that about a year ago, we wrote a bunch of fuzzers for a project, and after 6 months, the fuzzers found a high-severity vulnerability. And that's an example of the importance of this goal of fuzzing. At the same time, we also want to defend against malicious pull requests. We can do this in the CI by catching malicious code changes early, and we can set up the fuzzers to run continuously so that the code base gets tested every day via a project called OSS Fuzz, which I will get into a bit later. So how I fuzz Rekor, my main focus was on testing Rekor's processing and handling of the artifact types. And to demonstrate this, I have so far written 18 fuzzers since November last year, of which 16 were targeting Rekor's handling of the artifacts. A quick crash course about fuzzing. You have two main components when you fuzz test a software application, a fuzzing engine and a fuzz harness. The fuzzing engine is responsible for generating the pseudo-random data that we want to pass on to the target application. Now, I say pseudo-random. It looks random, and it looks like garbage data, but in reality, decades of research have gone into finding out how you can generate meaningful pseudo-random data for the software application you are testing. So the fuzzing engine makes this pseudo-random data available to us, engineers or testers, in the fuzz harness. Rekor is implemented in the Golang programming language, and I've put up here a scaffold of a fuzz test for Golang. So the fuzzing engine makes the pseudo-random data available to us in the function signature here. I've highlighted data, and it is our responsibility as testers to take this random data and pass it on to the software application that we're testing in the function body. In my case, that meant that I had to take this pseudo-random data, create an artifact type, and pass that to Rekor's processing of the given artifact type. When Rekor handles artifacts, it does so using the artifact properties struct, as demonstrated here. And this struct looks as such. The most interesting part of this struct is the artifact bytes field, which contains the data of the artifact that Rekor is processing. Now, there are a couple of ways you can approach fuzzing or fuzz testing Rekor handling of artifacts. You can randomize all of this and pass it to Rekor. And that's a valid approach, but you can't depend on that alone. Because when Rekor processes an artifact, it carries out several steps that makes it very difficult for a fuzzer to generate valid pseudorandom data that will reach a deep or far into the call tree of the processing. Some of these steps are decompression and verifying specific files in the decompressed archives. So what Rekor will do is it will decompress the artifact that you are passing to Rekor, and then go through the files in the decompressed archive and read them and verify them. And that's a very high barrier for a fuzzer to reach, to generate valid compressed files with valid metadata files in them. It will be able to do that, but it will take a lot of time and it will be very slow in doing so. So it's not an effective way. So what we had to do was to take the structured data, take the random data and generate these artifacts, create valid files, create valid metadata files of these artifacts, compress them, and then get the bytes of the artifacts that we created. Now, I won't go into too much details of the internals of this, but I would like to say that all my work is available in the Rekor repository, and you can go and check how we did that. Next, when we had reached a mature level of generating valid artifacts, we integrated the fuzzers into OSS-Fuzz. OSS-Fuzz is a project run by Google, whereby you can integrate critical open source projects, and Google will run the fuzzers, dedicating excessive resources doing so. OSS-Fuzz, so some findings in the open source ecosystem have been found from the mere reason that OSS-Fuzz ran the fuzzers of these projects. And these stats here highlight why. So since 1st of January of 2023 until last Sunday, OSS-Fuzz dedicated more than 57,000 CPU hours for all Rekor's fuzzers. That equals to approximately 6.5 CPU years. And that's an extremely important piece of infrastructure when fuzzing the open source ecosystem, including Rekor. A couple of the findings that came out of fuzzing Rekor since November 2022, the most interesting was this security advisory that was released last week. It contains 2 security vulnerabilities for the APK and jar files. And the APK and jar files are exactly the type of artifacts that are very difficult for a fuzzer to get right. So APK files and jar files are more or less zip files that contain a bunch of very specific files, including the files that make up the artifact. And the fuzzers found that when Rekor would process these artifact types, Rekor would extract the files, the artifacts, and read specific files, metadata files of these artifacts. And in doing so, the fuzzers found a zip bump vulnerability in the processing of both of these artifact types. And a zip bump is a vulnerability where you receive a compressed data type and you decompress it and you you read certain parts of that extracted archive entirely into memory, for example. And if the file or directory that you are reading into memory is very large, you can cause denial of service by way of resource exhaustion. And that was the case that in Rekor, that APK files and jar files would be extracted, and Rekor would read specific files directly entirely into memory, which could cause denial of service of the Rekor server. And if we should threat model that attack vector, it would look like this. On the right, we have a Rekor deployment, and on the left, we have users interacting with this Rekor deployment over an internet connection. And a malicious actor would be able to send a malicious APK file or jar file, cause the Rekor server to be unavailable because it would exhaust memory. And when a legitimate user would then interact with the Rekor server, it would be unavailable, and they would receive a 404. And an attacker could leverage this to cause other damage. For example, if a user would not be able to verify a given artifact, they wouldn't be able to consume it, and they might be forced to consume an old version of the given artifact. So that was the work on Fuzzing Rekor. Thank you very much.